Now, in order for us to evaluate the second law of Newton's, we have to know the equation that we're going to use is summation of force in S coordinate system. This one is equal to mass times the acceleration in S coordinate system, mass of fluid. Right. So here we have mass equal to the density times volume, and this one is equal to rho ni density times the cross sectional areas times the length, right? Let's say the length is S, right? So we have this geometry, the length is S, right? S as the length of mass of fluid as it moves. Okay, so we have the acceleration of fluid particle. This can be defined that the velocity in S coordinate system divided by time, right? So this is our understanding. So I just write here dv, right? dv per dt, and this is a differential equation, ordinary differential equation. So we can move this dt to the other side so that we can change the equation, or we can place the time here under m, sorry. So in deriving this equation, we're going to place the time period for the fluid to move from this location to that location. So we have as MAS is equal to M divided by dt times dv, right? So this one will become dm per dt, right? So it means that we just considered a small system in our case, and we evaluating it at a cross section. So this is what it means, right? The first concept that you learn is that we are looking a mass flow rate at a plane, right? So this is a mass flow. So this one is actually the mass flow rate. dV, right? So this is what we understood. Any question? Now we want to know how we can further elaborate this equation, the MAS part, the mass acceleration punya relationship. Right, so we have MAS equal to m dot divided by changes of velocity, right? So dv is the changes of velocity from here to there. We have v, and then we have v plus dv, right? So what does this mean? If you can expand this equation, actually v final velocity minus initial velocity. So when we derive this equation, we have v here, and then we have v plus dv kat situ, right? So v out minus v in. If there is a pipe, v out minus v in. So this is what it means. So what about mass flow rate? So mass flow rate you can evaluate at any location, right? We can evaluate at inlet, let's say rho v inlet, A inlet, right? Initial, I mean density, V final, A final. Or you guys can write it in the common form, rho V A. So if we have MAS, this one is equal to rho times cross-sectional areas, and then we have V, velocity at any location, and then dV, right? The velocity. Don't confuse with the volume. Now you just look at the left hand side. Now we are looking at the left hand side. This one, the force in S coordinate system when the fluid is moving, so it's subjected to the surface forces and the body forces. So surface forces due to pressure only, because we are consider very small volume, and then we have the surface forces may be acting in that direction, right? So this one due to the dynamic viscosity or viscosity of fluid. The other one will be the weight. So for this case, we only considered the weight of the fluid, right? So we have P plus dP A, cross-sectional area here, right? And then we have the P A, right? Now it is very difficult and very complicated because they're going to involve trigonometry. If I considered this geometry, right? So it's very difficult. So I'm going to assume that this fluid is moving upward, right? So it's much more easier because we can align with the gravitational acceleration vectors. So we're going to assume that the fluid particle is moving. This is a S coordinate system. Let's say this one is S equal to 0. This one is S approaching infinity, right? Negative infinity. S approaching negative infinity. S approaching infinity, right? And it is in the orientation of gravitational acceleration. So that one is easy for us to evaluate. So we have pressure here that act on A. So this one actually we can represent it by the cross section, right? Cross section there, and then this fluid particle. Then we have another there, pressure, and the fluid is acting on that position. So this one is P plus dP, dP times area. Okay, this one is minus the weight because the unit is in newtons. Right, and this one is equal to rho A V dV. And this one is dPA minus rho volume times G. And this one, the volume is actually A times Z, right? And then this one is G. and then this one is rho A, V velocity changes. So we can cancel A, right? So that we have a different form, dp A into, and then we can place the yeah, I think this is enough. So we just rho G Z or dz, right? So let's say the location here is very small. The size, we just look at the very small changes in the system, right? So what we need to do is to do the integrations. If you look at this equation, right, so in deriving this, so we need to do additional assumption here. We just say that the dp here is minus, very slow, right? So we get this minus dp. So we can have a 0 there, and then we have integration of dp, sorry, plus integration of rho v dv plus rho g dz, right? So we can do the integrations. So this one based on p, this one based on v, this one based on z, right? So finally we have obtained the same expression that we get before, in terms of pressure, in terms of heat, in terms of energy. But the thing that we have to know to understand about the this Bernoulli equation, where we get these values for P, right? This P it come from the surface forces. The velocity here, it tells us about the net force, right? So this one is actually the net force. This velocity, but if you are using energy balance, this come from the kinetic energy changes of the fluid, and this one come from the weight of the fluid if you are looking from the Newton's law of Newton, right? So this is what it means when we look at this Bernoulli equation in perspective of Newton's second law. Let me ask. No message there. So this is what it means when we try to compare Newton's second law with the energy balance. So if you look at the if you treat the problem as an open thermodynamic system, then you can explain further that the Bernoulli equation can be seen from a different perspective.